the one I'm going to be talking about today is computer vision plus social distancing. So how can these two technologies come together, and how can we help to ensure that we adhere to social guidelines around the coronavirus pandemic, but also introduce some artificial intelligence and some cool technology as well. So I'm Tom Farrand. I'm a deep learning engineer with IBM, and I've worked in my current role for about 18 months, mainly focusing on how we can knit together client problems with IBM solutions to deliver real value. And so this was a little kind of, I guess, side project that I thought would help to frame some of the power of technology, of power of computer vision, alongside a real current issue that's being rolled out and tackled as we speak. So why should we care or use computer vision for social distancing? I think there are three main factors in this. So automatic feedback is definitely one of them. So the computer vision algorithm can passively monitor film or video feeds and essentially provide notifications or feedback to either an operator or the people breaking the guidelines automatically and in real time. So there's no human intervention required. The system is completely closed, and that helps to really drive down those ongoing costs of implementing something. There's then the fact that it would use existing infrastructure. I think in one of Mike's slides, he showed about the number of cameras for surveillance are going to increase from 770 million to 1 billion. And so this infrastructure is out there, it exists, and we can piggyback on that, on the back of that, with computer vision solutions, and make use of that data which is accessible to the enterprise already. And speaking of accessible to the enterprise already, this makes it fast to deploy. So we can implement some fairly universal computer vision techniques, and we'll come on to those in a little bit, and make use of already existing infrastructure and already existing data. So it's a real nice use case and story for some companies who are trying to open back up. Typically, we've seen a lot of interest with manufacturing clients, and they're trying to open back up, and this is a really easy route to implement social distancing without having to wait for new kind of wristbands or other bits of kit that have been proposed to enforce social distancing as well. So throughout this, feel free to drop questions in the chat or come off mute and shout at me. That works as well. I'm willing to take questions on the fly. So how can computer vision be used for social distancing? And we're going to go over the basic workflow and consider some of the challenges that we have to overcome in this. And for the most part, it breaks down into two steps. So we're going to detect people, and we'll talk about how that works and why that's necessary, but hopefully it's fairly obvious that we need to pick people up out of the imagery. And then we're going to estimate the distance between those people. And surprisingly, it's actually the second point, which is slightly more difficult. I mean, kind of 20 years ago, the people detection would be a 10-year research project with requiring like 4 different PhDs. Now it's something that we can do very easily, very out of the box, and it's actually the second point which gives us more grief, but we'll come on to some of the tricks and estimations we can use to get around that. So for my solution, for the people detection, you won't get any medals for guessing that I used an IBM product. The IBM product was actually the IBM Visual Insights tool. And for those who may not be aware, this is a computer vision based tool that allows business users to train computer vision models. So it has a nice graphical interface and allows you to follow these 4 high-level steps very, very simply. And out of the back of that, you can train a model similar to this one. So this is actually a screenshot of the model that we trained in the tool. So it was this crowd human detector. You can see that the kind of model metrics, the accuracy, the mean average precision, the recall, the intersection over union, are all very, very high. This actually implies that we've overfit. So we haven't supplied enough data, and essentially our model has memorized our data. And so that's really bad for when we actually test it on new data, because it's likely not to be able to predict on the new data very well. But for the case of a proof of concept for a kind of MVP, this was enough. You'll also notice that we trained it on like a head detector. So we didn't actually do the full body of people, but we decided that in a crowd or a busier environment, you're more likely to see just the head of people as opposed to the full body. And so if we're actually evaluating the full body of someone, it may be occluded, or it's more likely to be kind of blocked by someone else. And so that might reduce the accuracy of everything. It also neatly means that we can tie two use cases together. So we actually trained it on two different classes. So it was taught to detect objects, or the object of a person with a mask and just a regular person. And so this means that we can perform a basic level of PPE detection while doing this social distancing use case. So it really is two birds, one stone. And this was made very, very simple to train, deploy, and then manage within that graphical interface of the IBM Visual Insights tool. So now that we've got a person detector, we're actually going to tackle some of the more trickier stuff that unfold when we try to estimate the distance between people. So there are two main challenges that we need to overcome. So from our 2D imagery, we need to figure out a 3D perspective in order to determine a bird's eye view and use that to estimate how far different people are away from away from each other. So we need to go from 2D to 3D. And that's actually solved with a technique called homography, which we'll talk a little bit about after this slide. We then, once we understand where people are in this bird's eye view, we need to say, okay, Tom and Ed are 500 pixels away from each other in our video footage. What's that in centimeters? What's that in feet and inches? So we need to convert pixel distances to real world distances to actually make it useful, because unfortunately the government doesn't put out social distancing guidelines in pixels relating to every single CCTV camera. So we need to make that conversion to make it a usable piece of kit. So getting a bird's eye view is homography. So, you can all read the definition there and like me, take absolutely nothing away from it. So we won't use that. But homography is essentially a mathematical technique of changing the perspective of one image to a different one. So what the perspective we have here is, on the left, we've got our input image, and this is actually of Oxford town city centre before the pandemic, which is why it looks so busy. And then this estimated output is something that we kind of guess at using what's called the homography matrix. And the homography matrix, all it is just a square of numbers. So it's just 3 rows and 3 columns of different numbers. And we can multiply any point in our image to create a transformed perspective of our bird's eye view. So when we open up our tool, we actually have the user calibrate the video feed for the first time. And they essentially just click a rectangle that's in perspective with the rest of the image. So we make use of the human knowledge there in the initial setup. And then the tool uses that to transform the image to a bird's eye view using this homography matrix. So again, user adds 4 points to the image, and that's used to estimate the bird's eye view. And the homography matrix we're going to use anytime we detect someone to transform that detected person to our bird's eye view, so we can plot people on a little map. So now that we've kind of figured out how to take an image and convert it to a bird's eye view, we still need to solve this problem of saying, okay, I've detected this fella in the middle with his bike. I've drawn a circle around his head. But how big should I draw that circle? How wide should it be to when my social distancing guidelines say 200 centimeters is the minimum distance between folks? So the answer to that is we actually use what we've detected as an estimation tool. So we say, okay, his detected head is, the bounding box around his head is 30 pixels in height. What we'll combine that with is the estimation of the average human head being about 21 centimeters from top of the chin to bottom of the chin to top of the head. And it's worth pointing this out. This isn't the only way to do this. A lot of people actually, if your client was looking for more a more robust and less kind of estimated way of doing this, you could actually measure things within the scene. The nice thing about this is the fact that there's very little calibration or setup if you were going to roll this out to a number of different kind of cameras. And so all we do once we've got our estimated and detected heights, we literally create a scaling factor. And so we can then go and say, okay, I want 100 centimeters. What's that, divided by our scaling factor to get it in pixel values, or multiplied by the scaling factor to get it in pixel values. So it's a really easy way of converting these pixel values into real world imagery. So if we put that all together and start to combine those different bits and pieces, we actually get our final result. I think Mike stole my thunder a little bit by having the GIF playing in the intro, but essentially you can see on the image on the left hand side where we've got our transformed bird's eye view. If you look closely at the kind of top of that bird's eye view, you can see that the ellipses are kind of distorted. They're not exactly circular, and that's just a fact that because we're estimating the bird's eye view from a 2D image, we have to there is always going to be some error in our method. And then on the right, you can see the little green circles turn red whenever they clash with someone else's circle. So that's the automatic feedback that I talked about before. Everyone is notified when they've breached social distancing, and it's immediate as well. So that was my whirlwind tour of computer vision with social distancing.